Hello everyone. In this video we will discuss about least square solution to regression problems. Especially we will be seeing about multiple linear regression model and polynomial regression model. Usually the solution for these two models ends with a least square solution. We will see two different types of derivations of how we obtain least square solution as a solution to both these models, and we will see the differences in the way it is derived and the related concepts. So let us start with the multiple linear regression model. As you can see here, there are m independent variables x1, x2 and so on xm, and one dependent variable y, and our goal is to find out w0, w1 and so on wm, which are the parameters, and this whole equation represents a hyperplane, and our goal is to find these model parameters w0 and so on wm. Whereas in multiple polynomial regression model, we are supposed to find out the best nonlinear curve for the given set of input output points, and where m is the order of the polynomial. So our job is to find w0, w1 and so on wm in the case of polynomial regression model. So as you can see, as you can observe that in both the models, our goal is to find the model parameters, and moreover, when what we do mathematically is also similar in both the cases. We have during the training stage input and output points, and our goal is to fit a best function. In MLR, our goal is to find a best hyperplane, and in polynomial regression, our goal is to find the best polynomial curve of a certain order m. So in both the cases, we have points which are away from the predicted line, and there is an error, and our job is to minimize that error and obtain the parameters for both the models. So we encounter an expression which is epsilon I is equal to yi minus yi cap, where yi cap is the points on the predicted line or curve, and whereas yi is the actual point given to us. So both of them comes under the category of supervised learning. So we have both input x and y's, and our job is to find out the best model parameters, and in turn find out the best line or a curve which approximates this relation between input and output. So this is what is our goal: minimize a function, objective function, and find out the model parameters w1, w2 and so on wm. So let's see how, when we try to solve this problem, we encounter a least square solution. So first let us represent in the form of a matrix. So let's take both these problems. So this is what we are supposed to minimize. Error epsilon is the error, and when you have in the vector form, and our goal is to minimize the L2 norm of this epsilon, and that epsilon is represented in the matrix form as y minus xw. So we'll find out how this representation comes in, and then let's see how we can solve this minimization problem and obtain the solution for these two problems. So for the case of multiple linear regression model, our goal is to compute the error between the actual points yi and predicted points yi cap. So yi cap is represented using these two matrices. So for example, epsilon 1 is y1 minus y1 cap, whereas y1 cap is represented using this predicted point. So this is the point which has been given by the MLR model, whereas this is the actual point y1. So in this way we do it for all the points, all the n points, and we represent in the form of a matrix. The same thing we do for polynomial regression model also, where we compute the error between yi and yi cap. Yi is the actual point, here y1 is the point, and the corresponding y1 cap would be the point on the mth order curve, which is 1 into w0 plus x1 into w1 and so on x1 power m into wm. So we take y1 minus y1 cap, and we represent this whole, both these models in the form of a matrices, and we can clearly see that mathematical error representation is similar in both the cases, and therefore our job is to solve this error between yi cap, y and yi cap, or y and y cap, and minimize the error, and we choose L2 norm as the objective function to minimize and thereby find the parameters. So our goal is to find this W such that this whole error is minimum. So let us see how we can find it. But before we go, we see that for solution to both these problems will result in what is called as least square solution. So let us see the derivation, two different derivations of how we get this least square solution for both these models. So let us start with slightly easier approach, which is a linear algebra based approach, where we exploit the principles of orthogonality, error orthogonality, and try to derive this equation. So let's take the system of equations. Y is equal to xw. Our job is to minimize the error between them. So for n much larger than m plus 1, this represents a system of overdetermined system of linear equations, and usually we find the case of no solution, and our job is to find the best, our job is to obtain best solution for the overdetermined system of equation, and that exactly what we are supposed to do in the previous case, where we are supposed to minimize the error between y and xw. So we, our one of the important property in linear algebra is this error term y minus xw is orthogonal to the column space of x. So if you see this x is nothing but the matrix which spans a certain space, and our y vector which is not in the space of x, and therefore there is an error between, or therefore you cannot span y by using just x column vectors. So the error vector is represented as y minus xw, and this error vector is orthogonal to the space of x. So we'll be exploiting this property to derive the equation for w. So since orthogonality, there is an orthogonality between error and the x, we can represent something as follows, where x transpose is a matrix, where and y minus xw is the vector. So orthogonality implies the dot product between them will be equal to 0, and therefore when you derive, when you expand this equation, we get x transpose x w is equal to x transpose y, and w is equal to x transpose x whole inverse x transpose y. And this is one simple way of deriving the solution for both the problems of multiple linear regression and also the polynomial curve fitting. So let us see a second approach where we use calculus based minimization approach to find the solution for w. So let's take our error function, which is the L2 norm, and when you expand this error function, we have y minus xw L2 norm. So when you further expand it, we represent in the form of transpose, and we multiply it, we get, when we apply transpose to individual terms, we get something as follows, and when you multiply it, we get something as follows. As you can see, second and third term are nearly similar, and therefore we can write it in the form of 2 into w transpose x transpose y. We employ some of the vector properties to simplify this equation. As you can see here, A transpose B is equal to B transpose A. We have exploited that to derive this final equation. And finally, our goal is to minimize this J of W. To minimize it, we have to compute the gradient and equate it to 0. So in order to compute the gradient, we, as the W is a vector, we do a vector differentiation and we compute the gradient. So when you do the vector differentiation by using these properties, we obtain x transpose x w minus x transpose y is equal to 0. And when you finally send x transpose x to the other side, we have w is equal to x transpose x whole inverse x transpose y. And the important thing is this matrix x transpose x, it's a square matrix, but it will be invertible only when x is a full rank matrix. So our assumption is the overdetermined system of equations, and the matrix x should be a full rank matrix, only then this is invertible. So that's how we find the least square solution using error minimization, using calculus, and we have seen earlier how we can derive the same solution using a linear algebra based orthogonality principle.